The average value is a calculation where we look at all the y values that a curve takes on an interval, and we literally calculate what the average of all of them is. Now, it's not like we're adding all the infinite numbers together and dividing by infinity, but instead using the area under the curve to calculate of all these y values the curve takes on, what's the average of them. Now, we accomplish that by finding the average height. So for instance, we begin by using the definite integral, and we can calculate the exact area under the curve, which means we're going to calculate the exact area of this region right here, again bounded by the curve and the x-axis. Now we're going to use this area under the curve to find the average height. So we imagine that the region we found here in red is spread out evenly like a rectangle. And because we know the overall area here in red, and we know how wide it is, what we look for is what single value, what height of this rectangle multiplied by our given width will be the same as this red area. So again, taking that overall area of the curve and just laying it out evenly underneath this. And whatever that is will be this average value right here. So of all these y values the curve takes on, that single value giving us the same area will be the average of all of them. Now, the way we do the calculation is we take that overall area under the curve, and because that equals our base times height, and we know the base, we just take that area and divide the base over. So we take our definite integral, which is the area under the curve, and by multiplying by 1 over the base, we essentially divide by it. This solves for that single value height. Again, that would be the average. Now, this obviously in general is just thinking of it as area under the curve divided by the length. Okay, so we're still going to have that b minus a feel to it, but that's geometrically what's happening to create this. So let's try an example. Let's suppose we have the graph of 3x squared minus 2x on the interval from 1 to 4, and we want to calculate its average value. So what we do is we take 1 over our b minus a, so in this case 4 minus 1, and then we find the area from 1 to 4 under the graph. So that means we're going to be doing the definite integral of 3x squared minus 2x along the x-axis. Now as we simplify this, that means the width of course is 3, so we'll be dividing by 3, or multiplying by a third. Now the antiderivative is going to be x to the third minus x squared from 1 to 4. And then we just work things out. So we're taking 1/3 of the value of this definite integral. So plugging in 4 gives us 64 minus 16, and plugging 1 in gives us 1 minus 1, and when you simplify all that and put it together, we get a value of 16, which means that on this parabola right here, 3x squared minus 2x, of all the y values that it produces from 1 to 4, the average of them is 16. Now, moving forward, it's important that we understand how to use the graphing calculator to help us evaluate definite integrals, especially as we look at more advanced applications and maybe dealing with more complicated functions. Now, it's important to understand that the TI-84 can evaluate a definite integral. So it can punch this all up and give you that exact area as a numeric value. But it cannot just do antiderivatives. So you can type in an indefinite integral and just look for that general antiderivative. It can only do definite integrations, and when you type this in, it'll just spit out the number. Now, in order to do that, we have to use some special commands in our calculator. We want to make sure we write our answers the right way. So the way we type it in our calculator is using the math9 command. And this, of course, brings up an exact definite integral, as you can see here. Now, another place to get this, as always, would be going to the alpha window, the F2 menu, and that would be the fourth option, since many of the math things are there. But the quick, easy way to do it is just to hit the math9 command. Now, we're going to type it in exactly as we see it. So we'll go from 2 up to 4, and then we type our expression in, so negative x to the third, and then that'll be plus 5x squared. Now don't forget to put the x there because it's got to match exactly as we have, but when I hit enter, it'll give me the exact area under the curve. Now the way we want to write our answers, typically with all these sort of problems, are improper fractions. So while this is fine as a decimal, right, we want to make that happen. So to do that, we hit our math key, and the very first option is to convert to fractions. So hit enter, and then hit enter, and it will give us an answer of 100/3. Now, another thing to keep in mind is that we can do the same thing, but especially in situations where we have to type this expression a lot of different times, we can save some time and effort by putting it somewhere else in the calculator. So we're going to do the same thing, but this time, before we begin, let's go to y equals, and let's type it in here. Now, by putting my negative x to the third plus 5x squared in y1 and storing it there, I can go back here and do my math without having to continually type this over and over again. This is especially helpful when this is a very complicated function, one you don't want to be typing over and over again, because that way you might make a mistake, but also it saves a lot of time. So again, I'll hit math9, put my limits of integration in. But this time, instead of typing the whole expression out, I'll simply tell the calculator to use whatever I've typed in y1 in that place. Now to do that, we'll go to the F4 menu. So we hit alpha F4, and that y1 is what we want. So we arrow over, put an x there, and again, when we hit enter, we get the same answer. And by hitting math, enter, enter, we can convert it right back over to what we want. So moving forward, these are things we can use as we are allowed to use a calculator with more advanced problems to do our work for us. It's our job to set up the definite integrals and know how the calculus does the work, but this is how technology can make it more efficient for us. Now, one of the first things we want to talk about when applying definite integrals is the net change theorem. This is the idea that if you know the rate of change of something and you find the area underneath it, it will give you the net change of that idea. So here we have the rate of change of our function f. This is a derivative, something like miles per hour or gallons per minute. Well, when you let something like miles per hour go for a certain amount of hours, you end up getting miles, right? You see how much things changed. So by looking at the rate of change over an interval, you actually end up with the net change. It's telling you how much that, amount, whatever it may stand for, changes on that time interval. So to give you a more concrete example, this rate right here could be something like miles per hour. And when I find the derivative and multiply it times hours, that means, when we take miles per hour times hours, you get this net change. And more importantly, this net change here is measured in hours. Now, this can apply to many different things, but the idea is that when given a derivative, right, a rate of change, and you find the area underneath it, it calculates how much that function, whatever you're describing, is changing. Now, you may also be asked to find the total change. And what you do with that is simply take the net change, how much it increased or decreased by, and then simply add in whatever it started with. So there's sometimes situations where they're going to tell you, hey, here's the rate, how it's changing over a time period, but they also might mention, listen, we started with blank amount. And when you have that amount, you can simply add it on to the net change to say total, how much happened and how much changed as we went. So let's look at an example. Here we have a ski resort that has a snow machine that adds snow to a ski slope. Now, over a 24-hour period, the amount of snow that's added in cubic feet per hour is modeled by this function. So capital S is going to be our function for the amount of cubic feet for snow per hour that's being added onto the slope. So the first question is, how much snow was added to the slope during the first 4 hours? Now, this is simply asking for the net change in snow, how much was added over that time period. So because S of t is the amount of snow, right, in cubic feet, per hour, this is right here the rate of change. So if we integrate that, right, from 0 to 4, which is the first 4 hours, that's basically finding the area under that curve. Geometrically, we're taking this right here, which is cubic feet per hour, and multiplying it over the time period, hours. So that means whatever the answer is going to be measured in cubic feet, which is what we want. We want to know how much snow, which would be cubic feet, was added during that time period. Now, in my calculator, the first thing, of course, I'm going to do is I'm going to go to my y1 and I'm going to type in this function. And I'm going to do that because I'm pretty much going to use this several times, and it's easier if I take my time and, type it in one time perfectly so I don't make any mistakes. And as you notice, you got to be really careful with your grouping symbols. So we have 24 minus x times the sine of 0.071x quantity squared. I know the squared here is a little shortcut to reduce grouping symbols, but in the calculator, you do have to give them. So double check you typed it right, and now that we have this in there, we only need to do it once. So to do this question, we'll simply say, math 9, we're going to go from the 0 to 4 hours. And because I have the whole thing typed in my y1, I can put that in there and get the answer. So in this case, the amount of snow that was added during the first 4 hours is going to be approximately 95.683 cubic feet. So we'll put that 95.683 cubic feet. Now here in part B, we want to calculate the amount of snow that was added to the slope in the last 2 hours. So what that means in this problem is that we're going to do the same thing. We're looking for a net change, but the time period is different. Remember, the rate at which the snow is being added is modeled by this function, which isn't always the same. So obviously, depending on your time period, you'll get a different amount of snow. Here, because we're looking at the last 2 hours, we want to integrate from the 22nd hour all the way to the 24th hour to be those last 2 hours. And again, we're going to find the area under the rate of change of the amount of snow. Okay, so that's our cubic feet per hour. And when we calculate the area of the curve, we're going to get, again, an amount in cubic feet. So let's go ahead and grab our calculator and do that. So we hit math 9. We'll go from, in this case, 22 up to 24. Again, let's grab our function we've already typed in there in y1 and punch it up, which means that during the last 2 hours, the amount of snow that was added was 2.260 cubic feet of snow. Now in our third example, we're going to look at the average rate at which snow was added. So this is basically saying the average of this function. Now it's a little confusing when they say average rate because it almost sounds like average rate of change, but it's not. It's saying the average rate, and a rate is the value of this function. So this is just another way of saying average value, which is what we did earlier. So that means we're just going to calculate the average value of this function during that 24-hour period. So because that 24-hour period has a beginning at 0 and endpoint at 24, it'll be 1 over 24 minus 0, and then we'll integrate over that full 24 hours to get the full area and divide it by its width, okay? Now, what's important to understand is the label of this. Now, like we did before, this definite integral right here is going to calculate the amount of snow, right, that was added over the full time period, and that would be, of course, measured in cubic feet. But because we're calculating average value, we then divide it by that width, which is time. So even though this cubic feet per hour becomes simply cubic feet here, dividing the time takes it right back to cubic feet per hour, which makes sense because we're asking what's the average rate at which the snow is being added. Obviously, the amount of snow at any given time being added on is changing, so we want to take that 24-hour period and just say, on average, how much snow at any given time, how fast was that being added. So again, we'll take our calculator and just punch this up. So we'll take 124, okay, because that's obviously what 24 minus 0 is, times our math 9, and this time we'll do the entire time period 0 to 24. Okay, we'll go ahead and grab our y1 and hit it. So right now we're going to get about 15.043. And again, what's important to remember when I have this 15.043 is that this is the average value of s. It has the same label because while the definite integral just made it cubic feet, divided by the width puts that hours right back. Now let's look at a different example. Here we're going to look at visitors that are arriving at a national monument at any given time for this 20-minute time interval, okay? And that's being measured in visitors per minute on those minutes. Now the other thing that's important is that time 0, or initially, there were 42 visitors at the monument. So they're giving us that initial amount that we'll use later. So the first thing I'm going to do, of course, is grab my calculator and type this in. So here I have in my y1, so we'll store that and just go ahead and make sure it's ready to go. So let's go ahead and start the problem. The first question begins to say, well, how many visitors arrived at the monument from the time period of 5 to 10 minutes on this interval? So that means we'll simply look at the amount, so from period 5 to period 10, of our rate. And again, this capital F of t is the rate at which visitors are arriving. So we find the area underneath it, it will give us the amount of visitors. So we'll take our calculator and punch this up. So we'll go from math 9. Okay, so we're going from 5 to 10. And as always, we'll grab our thing we typed in y1, put our x there, hit enter. So it looks like we have about 206.348 visitors. Now the next question asks, well, how many visitors are actually at the monument at time t equals 20 minutes? Now what that means, of course, is that we have to begin with how many we started with and then add on the amount that were added again over that 20 minutes. So to do this problem, we'll begin with our initial amount of 42 visitors and then say, well, how many were added onto that from 0 to 20? So we'll take the rate at which visitors were arriving, multiply that over its time period to give us the change in visitors, but again, plus the initial amount to get that total. So we have to take our calculator and retype it this way. So let's do 42 plus math 9. We're doing the entire interval, so we'll go from 0 to 20. Okay, put our y1 in there, and it looks like at the 20 minutes when that roll over, we have a total of 775.265 visitors. Now this question is very similar to the one we saw before. We're looking for the average value of the rate. So again, we're looking at this f of t and just saying what is its average value. And we're looking at it from the time period of 10 to 15 minutes. So in this case, we'll be taking 1 over 15 minus 10. So that's how wide that region is. We're beginning, of course, from 10 to 15. And we'll plug our f of t dt in there to get its average rate. So let's go ahead and punch that up. So this would be 1 divided by 5, because that's obviously how wide it is. We'll multiply that times our math 9 command, and we're just going to go from time 10 to time 15 on that interval, throw our function in there, and that's going to tell me that as I do this, let me make that next, as I do this, that means the average rate on that time period is 39.766. And remember, when I write that 39.766, this is still going to be measured in visitors per minute, because while we did calculate the amount of visitors, we averaged it right over that time period. Now, this last question looks very, very similar to what we just saw. We see this word average, but instead of saying the average value of the rate, this is the average rate of change. And whenever you see average rate of change, this takes us back to our, idea of just rates of change, whether it's be the derivative or slope. Remember, the instantaneous rate of change is the derivative, but the average rate of change is slope. So when we see this, we don't want to confuse with finding the average value or the average rate, but this is the average rate of change, and that of change really makes a difference. So what we're looking at is saying from 10 to 15, what's the average rate of change of the rate? So kind of like what's the slope of f of t on this interval, okay? So when I set this up, I'm going to have to take the actual rate at 15 minus the rate at 10 and divide that over this. So as you can see, it is y minus y over x minus x. Average rate of change is just the slope. Now, we still can use our calculator to do this, but we're not using an integral. So let me show you how to type that in. So in our calculator, here's what's going to happen. We'll make a fraction. Now, we want to evaluate the equation at 15. So what we're going to do is we're going to go ahead and grab that function y1, and right beside it, we'll just go parentheses, 1, 5, parentheses. What this does is tell the calculator to plug 15 into y1. Now, we'll subtract the same thing. So bring up y1 again, and then we're going to plug 10 in. So this right here is basically y minus y, and the bottom we're taking 15 minus 10, or just get 5. So what that tells me is the answer is negative 1.518. So this is negative 1.518. Now what this means, of course, is that the average rate of change of this rate is a negative number. What that means is the rate at which visitors are coming is decreasing. So yes, they're coming and there's more and more people, but the rate at which they're walking in the door is getting smaller at that moment in time. So we have to be really careful how we label this. F, of course, on top is being labeled as visitors per minute, but we're further than dividing it by minutes. So this is going to be labeled as visitors, but it's per minute, or in other words, per minute squared, because it's the rate of change of this rate.